Good old M. Number 1. A book is sitting on a level desk. Which of the following statements are true? It's going to be a half mark for each one of these because 4 statements for 2 marks. True or false? There are no forces acting on the book because it's not accelerating.
False.
False. Now, because it's not accelerating, I can certainly say that the net force is equal to 0, so I can skip down and say part C is definitely true. B, the magnitude of the normal force between the book and the desk equals the magnitude of the gravitational force on the book. I think that's true. No extra forces. Friction is what's holding the book on the desk. Could a book sit on a desk if the desk was made out of ice, as long as the desk was level? Yeah, so false. FTTF. Number 2, this is a job for a free body diagram. What are the forces acting on M1? M1G, normal force number 1. Tension. M2G, normal force number 2. And tension this way, F applied this way. It wants the acceleration of the entire system, so I'm going to say, okay, F applied is winning, minus tension, plus tension. Does M2G and M1G show up in the equation at all? They are not in the same direction as the rope, so I don't care about them. They'll show up if I bring friction into the play, which I will later on. So it's going to be that equals M all A. And tension vanishes, and they want me to get the A by itself, so I'm going to divide by M all. I get A equals F applied. You know what? Let's go to numbers, Mr. Dueck. You already got F applied written there. 24 divided by 8 plus 12. 24 over 20. Oh, I can do that in my head. It's going to be 6 over 5. 1.2? Mm-hmm. So if you got 1.2 meters per second squared, I would give you 2 out of 2. Otherwise, I would probably give you 1 mark for that, half mark for the answers, for the numbers, and a half mark for the answers. So if I saw F applied over M all equals A, I would give you 1 mark. Find the tension. I'm going to find the tension from mass 1, because then my equation is going to be tension equals M1A. You could also go 24 minus tension equals M2A. Tension is going to be 8 times 1.2. 8 times 1 is 8. 8 times 0.2 is 1.6. 9.6 newtons, yes? Oh, let me pause for the video for a second. Number 3 is the same question as number 2, except I'm going to add friction. And when I first made this up and added friction, nothing moved, so I had to up the applied force to 50 newtons. So I'll do in blue what I would add for number 3. I would add, there is a friction force number 1, a friction force number 2, and that's 50. So now my equation becomes F applied is still winning, minus tension, minus friction force number 2, plus tension, minus friction force number 1. That equals M all A. A is, lose tension, is going to be F applied minus, friction is what times what? Mu times the normal force. I don't know the normal force. Which mg for friction force number 2? M2g. Minus mu m1g all over m1 plus m2. It's going to be 50 minus 0.12. What was the masses? Times 12 times 9.8 minus 0.12 times 8 times 9.8 all over 8 plus 12. Yep. Who's winning? 50 minus 0.12 times 12 times 9.8. Take away 0.12 times 8 times 9.8. Close off the top, divided by a bracket 8 plus 12, or you might have been just put a 20 down there. Do you all get 1.324, 1.32? I got a positive answer, so I guessed the right winner. If I got a negative answer, I would say, oh, friction is in the winning direction. It doesn't mean it's accelerating to the left. It means probably nothing's moving in this case. 1.32 meters per second squared. If you got that right, 3 out of 3. Otherwise, I would give you 1 mark for the original equation, 1 mark for getting the A by itself, 1 mark for the answer, or something like that. Find the tension between the two masses. I'm going to use mass 1 because there's only 2 horizontal forces. Mass 2 is yuckier. So I'm going to go tension minus friction force 1 equals M1A. Tension is going to be M1A plus friction force 1. Tension is going to be M1, 8A, 1.32. I'm going to use my answer button, though, because I do have an extra digit kicking around here, 1.324. Plus mu times the normal force. I don't know the normal force. Oh, but look. I'm going to get tension equals 8 times 1.32 plus 0.12 times 8 times 9.8. Answer button. Plus 0.12 times 8 times 9. 0.8. Do you get, 20 even? Newtons. For 2 marks, I would probably give you half mark if I saw that, half mark if I saw that, half mark for the numbers, and a half mark for the answer. Ooh, elevator questions. This is a job for a free body diagram. I'm going to do a generic free body diagram. I'm not going to then worry about arrow lengths. I just want to remind myself that I definitely have gravity down, and since we're standing on a scale, there's a normal force up. Sometimes the normal force will be longer, Clarissa. Sometimes it'll be shorter, but here we go. We're accelerating up. Who's winning? I guess normal force minus mg equals ma. What's this question wanting me to find? Well, it's asking me to find the scale reading, but what does a scale read? Normal force. So I'm going to get the normal force by itself. I'm going to get normal force equals ma plus mg. It's going to be m 60 a 1.2 plus 60 times 9.8. This one I can do in my head. 660 newtons. 2 marks. I would give you 1 mark for that, half mark for that, half mark for the answer. What if the elevator accelerates downwards? Who's winning? This time it's going to be mg minus the normal force equals ma. Swappy dance, because I don't like the negative in front of the normal force. So I'm going to plus this to that side, minus that to that side. I'm going to get the normal force equals mg minus ma. The normal force equals 60 times 9.8 minus 60 times 2.25. Do you get 453? What if instead of asking you for the normal force in newtons, what if I asked you for what the actual scale was reading in kilograms? How would I convert this to a scale reading in kilograms? Divide by 9.8, and that would tell you what mass this person felt like they possessed. They feel lighter. Why in part C can I just go Why can I say that? And so I could go winner minus loser equals MA, but what's A? 0. So it's going to be winner minus loser equals 0. It's going to be winner equals loser. It's a tie. That's a long way to say it's a tie. So the normal force is just going to be 60 times 9.8. I can do that in my head. 60 times 10 would be 600, so it's going to be 10 minus 600 minus 12. 588? Mm-hmm. One mark, half mark, half mark. Oh, in free fall, mentioned I jumped out of an airplane. Yes? You could do a proof, but 0. If you stood on a scale, it wouldn't read anything. Has gravity vanished then? This is why I said a scale does not measure mg. It can't, because mg is very much still acting on me when I jumped out of an airplane. What does a scale measure? How hard the ground has to push up. No ground, no need to push up. Can you give yourself a lovely score, please, out of 19? If you need to lawyer with me, now is the time. What we're going to look at today is what we call the inclined plane. We're going to ask, what if the ground is on an angle? Did I say angle? Yes, it's going to be components, but we're going to be very, very clever. We're going to pick an unusual set of components. It's not going to be horizontal and vertical. Cole, can you make it quick? And then I want your focus up here because I don't want you zoning out. Whatever you're looking for. Can it wait? Let it wait. So here's the first thought problem. I want you to imagine that a person is standing on a ramp, standing on a Newton scale, standing on a bathroom scale, but we'll say it reads newtons, not kilograms, so we don't have to do the divide by 9.8 conversion, and attached to a rope. As the angle of the ramp increases, as this angle here gets bigger and bigger and bigger, what happens to the scale reading? Nothing, increases, or decreases. First of all, when I'm talking about scale reading, which force am I really talking about? Okay, so as the rope gets steeper and steeper and as the angle gets steeper and steeper, as the angle gets steeper and steeper and steeper, what happens to the normal force? Bigger, smaller, or stays the same?
Smaller.
Smaller? Convince me.
Because since it increases, we have more tension.
How do you know?
Because
Now, I'm going to interrupt you. I could do an actual lovely proof with angle theta and get shift sine or shift cos or shift tan and do a lovely graph. I'm going to give you another strategy. So I'm trying to give you strategies to use for these using principles of physics right to explain questions, because they will show up in the future. One of my strategies is to go to the extremes. What's the smallest angle I can have in degrees exactly? No, even smaller than 1. 0. Okay, I'm going to ask what happens when it's flat. What's the biggest angle I can have? 90. I'll look at those two, because I can probably analyze those easier, and then I'll just make the assumption that the transition is smooth. I'll show you what I mean. If we were on flat ground, let's write this out. If theta equals 0. That's about the shortest way that I can write out if we are on flat ground. What would the normal force equal? Now imagine the free body diagram. This is a job for a free body diagram. Pardon me? Okay, I think on flat ground the normal force would be mg. If theta equals 90 degrees, you know what? If we were at 90 degrees, I think this person would be dangling from the rope, swinging back and forth. What would the normal force read then? 0. So if we go from a maximum of mg to 0 as the angle increases, and we assume that the normal force doesn't just jump around at random magically, what did the normal force become? Bigger, smaller, or the same?
Smaller.
What do 3 dots mean? Anytime you see a therefore, make sure you know what it's there for. That's not meant to be a joke. That's actually in math proofs. We always said whenever you saw a therefore, that meant that the previous few lines had been building up. Go read it. Therefore, B. Matt, you okay with that argument?
Isn't it C?
Oh, C. Thank you. Now, are you okay with that argument, Matt? Candy for you. Matt, are you okay with that argument now?
Yes.
Okay. I'm almost out. Smarties seem to be not very popular. It's almost all Smarties down there. Wish I just taught a few more. Oh, never mind. Just looked up. Yeah, well, okay. Same question. Same question, but instead of the normal force, what happens to tension? You know what? Let's use the same approach. Let's ask what happens when theta equals 0. Let's ask what happens when theta equals 90 degrees. When theta equals 0, when this is flat, I'm imagining the rope would actually have slack in it, would it not? So what would tension be if the rope has slack in it? What about when we're at 90 degrees and this person is dangling from the rope? I can tell you exactly what tension is in my free body diagram. Tension is exactly the same size as? Yep. So this is what I was thinking, Matt. This is the B, increases. Therefore, B. So it looks like as the angle gets bigger, the force pulling you into the surface, the normal, gets smaller, because the normal force is a reactive force to that. And the force pulling you down the surface gets bigger, because tension is a reactive force to that. What the previous example shows is that for objects on a ramp, the force of gravity partly pulls the object onto the ramp, it squeezes it onto the ramp, and it partly pulls the object down the ramp. It makes it want to slide. In terms of the other forces, well, you know what? Let's do a free body diagram right here. What are the forces acting on this block? Get the obvious one. And let's pretend that friction is 0 here. So let's say that mu equals 0. What are the forces acting on it? Draw gravity nice and big. In fact, I'm going to strongly encourage you to always, whenever you draw mg on a ramp, go through the bottom of the triangle, and, ready for trick number 2, always put the mg on the opposite side of the pointy part. Sorry, on the same side as the pointy part, not the opposite side. Trust me. Otherwise, it's going to get in your way later on. What else? Now, Adam said normal force. Look up. This is not the normal force because the normal force is always at right angles to the surface. So the normal force in this case would be going up about like that. Okay. How are we going to break this up? We could make the normal force go vertical and horizontal, but instead it's going to be much, much easier for us to break up gravity. We're going to break gravity up into mg perpendicular. The symbol for perpendicular is an upside down capital T, two perpendicular angles. That means perpendicular. And we're going to break it up into mg parallel to the ramp. The symbol for parallel is two slanty parallel lines. What's pulling you down the ramp, Matt, is the parallel component. That's what's making you slide down the ramp. What's creating the normal force is the perpendicular component. So, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. It's mg perpendicular, not mg. Not mg. Oh, and if the surface is rough, there will be friction. So it says, draw a force diagram. By the way, the two blue forces here, that would be your free body diagram. Technically, those are the only two forces. The dotted lines aren't actually part of the diagram. I broke gravity up into components, but those are not extra forces on here. So it says, draw a free body diagram for an object that is sliding down a rough ramp. Okay. What are the forces acting on this block? Get the obvious one. Straight down. Put the mg on the same side as the pointy part. What else? There's a normal force at 90 degrees to the ramp, like that. Which way is this block sliding? Which way would friction be pointing then? What would friction be? Mu times the normal force. I don't know the normal force. Oh, but and don't say it's mg, it's not. We'll have to get into this. What if we were sliding up the ramp? Now, how could you be sliding up the ramp? Someone must have given it a big push and then walked away, and it kept sliding for a little while. What are the forces acting on it? Cole, get the obvious one. Your pen. What else? A normal force at right angles to the ramp. Which way is this sliding? Which way is friction going to be pointing? If you compare these two, the reason if you try sliding an object up a ramp, it stops so quickly, it's because this is slowing it down and this parallel component of gravity, which I haven't put in, is slowing it down. You have two forces slowing it down. It's going to come to a stop really quickly. Next page. So, which is the best free body diagram for a mass that is at rest on a ramp? A or B?
B.
Well, the good news is one of you is right. The answer is either A or B. Why is B impossible to be at rest? Because if you break gravity up into its components, you have an unbalanced force down the ramp. That cannot be at rest. A. And this is going to be Captain Obvious, but that's why you can't stand on a slippery hill. No friction. So in order to determine the size of these components, I'm going to do something similar to what I did last unit. We're going to do the trig proof once, and then we're going to come up with a stupid way to remember it in the same way we said dy was sine. We're going to come up with something stupid, okay? So here is gravity, mg down, and I've broken it up into components. Now, we're going to decide we're always going to draw all of our pictures identically. So you're always going to put the mg on the pointy side. The reason you don't put the mg on this side is then it ends up inside your triangle and it clutters things up. So you'll always put the mg on the pointy side. You're always going to do the perpendicular component first and then the parallel. If we do that, our diagrams will always look the same. And what we're going to try and figure out is where this angle shows up in that triangle. Which angle do you think it is? 3? Let's find out. First of all, here's our proof. Ryan, how big is angle 1 exactly as a number? Yeah, I just drew it in. How big is angle 1 exactly as a number? Loud and proud. That's why I put the 90-degree symbol there. Okay, so if you want to, you can all put that there, 90 degrees. You okay with that? Algebraically, how big is angle 2? What does every triangle add to in degrees? 180. We've just used up 90, so how many degrees is left for these two angles combined? What do these two have to add to? So I'm going to argue that angle 2 is 90 minus theta. If that front angle, that pointy angle, was 30 degrees, angle 2 is 60. If that front angle is 70 degrees, angle 2 is 20. If that front angle is 20 degrees, angle 2 is 70. You okay with that argument? Now, how big is angle 3? This is where you are at a disadvantage because you have seen very little geometry in the new curriculum. In the old curriculum, we did geometry, and we noticed that anytime you had a Z like that, this angle and this angle were the same. We called it alternate interior angles. Mr. Gerard used to jokingly call it Zangles because there was a Z involved. And so angle 3 is the same size as angle 2. How big is angle 4 then? I don't think it's the same as 1 because that would make it 90 degrees. It doesn't look... Oh, and why must it be theta? You ready? Do angle 2 and theta add to 90 degrees? First of all, do angle 2 and theta add to 90 degrees? Do angle 3 and mystery angle add to 90 degrees? Well, if 2 and 3 are the same, and they add to 90 with theta, then 4 must be the same as theta. So what we're going to do, are you ready, folks? This is your reward. We're always going to go color, 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 color. That top angle will be theta. We've proved it once, Chad. We never will again. Okay? So now let's do one with some numbers. Example 6. I'm sort of going to say I like example 6, except to be honest, it's too easy. I would give you friction or another force. Or ask you to find acceleration, then do something with it. After 6 seconds, how fast is the object traveling or something like that. But for now, okay. William, what does example 6 want me to find? You know what this is a good job for? Although, did they give me a picture? I'm going to label the picture. And I'm going to go very meticulously. What are the forces acting on this? Get the obvious one. And I'm going to draw a nice big gravity. I almost always like to go all the way through the bottom. That also gives you one more 90-degree angle as a little handy reference, which is good. Pause. Color, 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 color. I'm going to break this up into parallel and perpendicular components. I'm going to do the perpendicular first. Can all of you put your pencils down and look up? First, I'm going to draw these without dotted lines. I will draw them with dotted lines, but remember, the parallel has to be parallel to the ramp. So, tell me when to stop drawing perpendicular. I can't go like this. Some kids want to go all the way to the bottom, and then they say, there. No, that's parallel to the bottom. That's not parallel to the ramp. I couldn't go like this and quit, because that would give me that, which is not parallel to the ramp. So if you want to pick your pencils up and a nice dotted line, because this is a component, and I'm going to stop right about there. This is MG perpendicular. Then I'm going to go sound effects can help, MG parallel. The right angle is right there in this triangle. Color, 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 color. Okay. What else? So what are the forces acting on this? Get the obvious one, gravity. What else? Which way? Perpendicular. Not only that, I think the normal force is going to be exactly the same length as that, because that's what's causing the normal force. So the normal force I'm going to do in blue because it's an actual force, not a component, and I'll eyeball it, but I'll try and get it to be about the same length as that perpendicular component that I drew. What else? Is there friction? Is there a rope? That's it. William, what did this want you to find? Who's winning? Don't say MG, because it's not. Who's winning? MG parallel. Who's losing? It's a trick question. No one. If I had friction, that might be where friction would go as a loser once we get a little further, Matt, but no one. Matt, what does winner minus loser always equal? What we need to do is we need to find an expression for MG parallel. I'm going to redraw the triangle right here. Kind of looks like that, where that's MG. There's theta. I'll put a generic theta there as opposed to the 25 because I want to generalize. This is MG perpendicular. This is MG parallel. Just to make Adam happy, color, 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 color. MG, opposite adjacent or hypotenuse. MG, opposite adjacent or hypotenuse. MG perpendicular, opposite or adjacent. MG parallel. Now, you will know MG typically because you'll know the mass. So I'm going to find MG parallel using those two. Which trig function? Sine. I'm going to get sine theta equals mg parallel over mg. I'm going to multiply the mg here. What can I replace mg parallel with? Mg times which trig function? What can I replace mg parallel with? Mg times which trig function? Say it again. So this is what one of my students came up with a couple of years ago. It was a stupid way to remember this. She said, Mr. Dueck, the symbol for parallel is two lines, a sine. And I went, that'll work for me. Okay. Mg parallel is going to be sine. Two lines is going to be sine. Anybody want to guess what mg perpendicular might end up being? Of course you know the answer. Of course you know the answer. Okay? You could do the same proof and you'll find it is cosine. Worth sticking in your back pocket. Mg two lines is sine. But if you blank out, Haley, redraw the triangle and do the proof. So, mg sine theta equals ma. William, is there an m in everything on the left? Hey, yes. Is there an m in everything on the right? Is there an m in everything? Mass cancels. In fact, I could have canceled it on the previous line. I just didn't want to scare you. Really, what I could have said is g parallel equals g sine. G, two lines is sine, and the m just does its thing. This is the physics of skiing on a ski hill, because a ski hill is nearly frictionless. Does the mass cancel? That is why a grown-up can hold the hand of a little kid and ski next to them without the grown-up constantly having to adjust their speed all the time. Because if the mass didn't cancel, parents and children could not hold hands on a ski hill. Well, you could. You'd have to constantly be adjusting your speed. Now, I see Oscar kind of squinting a bit. I'm dumbing this down a little bit because we are representing your mass as a dot, and technically we're putting that dot right on the ground, and a grown-up would have a slightly taller center of mass. And so, yeah, mass doesn't quite cancel, and air resistance also plays a part. But in our magic physics world, where we're keeping the physics nice, this is what at least explains why it's doable. Okay? So, you can cancel the m out on this side if you want, or you can cancel the m out on the other side. What are we trying to find, William? We're done. The acceleration is going to be 9.8 sine 25. Not negative, we took care of that. Oh, and I knew it was going to be less than 9.8 because 9.8 would be if the hill was vertical. You get 4.14? meters per second squared. So what we're going to do, if you give me a ramp, is rather than adjust all of the other forces to match gravity, it's easier to match gravity. It's easier to adjust gravity to match all of the other forces by finding the perpendicular and parallel components. Example 7. I like example 7. I like example 7. Example 7 is a nice question. It says, consider this mass sliding down a rough ramp. A says, find the force of friction. Okay. You know what it was a good job for? What are the forces acting on this 5 kilogram mass? Get the obvious one. There's mg. Mg always goes on the pointy side, so it stays out of my triangle. Stop. I'm going to break this up into perpendicular and parallel components. I'm going to go d, 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 d. Change colors. I'm going to go d, 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 d. Stop right there. D, 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 d. This is going to be mg perpendicular. This is going to be mg parallel. The right angle goes there. Color, 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 color. Color, 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 color. And now we continue. Are we sinking into the ramp like quicksand? Are we flying off of the ramp like Superman? No, then there must be a normal force. How big? Right now, exactly as big as mg perpendicular. I'll eyeball it. About that big. Yes. What else? Friction. Which way? Up is incorrect. I gotta be fussy. If you say up, I think you're going like that. What, Adam? Up the ramp. Friction is up the ramp, and I'm pretty sure that friction is losing, so I've drawn it small. By the way, what's the tug of war here? Which two forces are having the tug of war? I'll give you a hint. One of them is friction and mg parallel. And so I looked at mg parallel, and Haley, I thought, I think we are accelerating down, so I drew friction smaller than mg parallel. How would I know that I had guessed wrong if I solved for acceleration and got what kind of an answer? Then I would say, oh, friction was the winner. I'm slowing down going down this hill instead of speeding up going down this hill. Who knew? A wants me to find friction. Friction is mu times the normal force. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force, and it ain't mg. Which force is the same size as the normal force? Friction equals mu mg perpendicular. Which trig function is mg perpendicular going to be? Sorry? I thought somebody said it. Of course it is. Common sloppy mistakes. By far the biggest one that I see, look up, because kids are so proud they got the coast. You should have seen Cole's face. He was, oh, I got the cosine, I'm so good. And somehow on the next line, they forget to put the G in, because I don't know, but that's common sloppy mistake that I see very often. And so if your answer is way off, like way too small, especially if it's off by a factor of about 10, because 9.8 is close to 10, go double check. You might have forgotten to put the G's in. Okay? Okay. Point 2 times 5 times 9.8 cosine of 35. You get 8.02769. I'll go 8.03 newtons. What was that? Nothing? Okay, good, shut up. Okay. There's A. Nick, what's B want me to find? You know what it was a good job for? What are the forces acting on? Oh, we already got our free body diagram. Who's winning? Gravity is not winning. First of all, please give it to me from the free body diagram exactly how I labeled it. Good. Now, if in your homework you can take the next step, Nick, I won't freak out, but let's in our notes meticulously so we're studying what the heck we did. Yes, MG parallel. Who's the loser? And that equals MA. Now, I know friction is 8.03, but I want to do this one algebraically just to look for some patterns. So MG parallel, Nick, which trig function is 2 lines? So this is going to be mg sine theta minus mu times the normal force. I don't know the normal force. Oh, but look. mg perpendicular, which is which trig function? Of course it is. And that equals ma. Nick, is there an m in the very first term? Is there an m in the middle term? Is there an m in the last term? Is there an m in everything? Can grown-ups and little kids ski on the same hills together? Yep. And so I end up getting A equals g sine theta minus mu g cos theta. Okay. And the reason I'm doing this is there may be a question in your future where I don't give you the mass. In fact, there will be one. And kids always freak out. You didn't give me M, Mr. Dueck. Probably because it cancels. Now, if you're not sure, make up a nice mass. I'll let M be 10 kilograms. And even if it did cancel, everywhere you multiplied by 10 in your work, you'll end up dividing by 10 later on, and you'll still end up canceling with numbers. So you're okay. For now, A is going to be 9.8 sine 35 minus 0.2 times 9.8 cos 35. And I get 4.02 meters per second squared. Turn the page. I like example blank, I like example blank, I like example blank. Example blank is a nice question. Did I go too fast, Brandon?
No.
Okay. Okay. Hey, what's this question asking me to find? Hey, what's mu? I don't know. What's mu with you? Yeah, it's asking us to find the coefficient of friction. Okay. Did they give me a picture? I'm going to doll. And if I could give you one piece of advice, don't draw a small triangle. Every year I see some kid who insists on drawing a triangle like this, and they can't figure out why they keep getting the wrong answer. Draw yourself a fairly, in fact, really big triangle. It makes the sides easier to read. So I usually have the ramp going downhill to the right. Theta is 21 degrees. There's the block. What are the forces acting on it? Get the obvious one. Really?
MG.
Thank you. Wow. Again, I tend to go all the way through the base, so I have an extra right angle for reference. MG always goes on the pointed side. Stop. Break this up into its components. The right angle goes there. This is MG perpendicular, MG parallel. Now I can continue with my usual routine. Are we sinking into the ramp like quicksand? Are we flying into the ramp like Superman? No, you say. There has to be a normal force, and it'll be the same size as mg perpendicular. Which way must friction be pointing? And we're going to be finding a mu. Technically, we're finding a mu static, but I told you I wasn't going to care about the two different types of mu, but in case you're asking. And you know what? Why did I draw my friction force exactly that long?
Like mg.
Trying to eyeball it, make it about the same same length as mg parallel. And in fact, that's my equation. I could say who's winning, who's losing, but are we accelerating at all, Maggie? Then it's a tie. What's it a tie between? Up the ramp and down the ramp. It's a tie between mg parallel and friction. Friction is what times what?
Mu mg perpendicular.
Mu times the normal force. I don't know the normal force. Mu mg perpendicular. Mg parallel. Two lines. Which trig function? Mg perpendicular. Which trig function? Of course it is. Ooh, Ryan, is there an M in everything on the left? Is there an M in everything on the right? Okay, that's kind of... Ooh. Is there a G in everything on the left? Is there a G in everything on the right? Okay. What are we trying to find? Let's get the mu by itself. I think it's going to be sine over cosine. Now, the fact that the G's canceled, here's what that means. This would also work on the moon. If you had Star Trek teleportation technology and you beamed this to the moon, it would still stay at rest. Or if you beamed it to Mars, it would still stay at rest. Or if you were near a black hole, it would still stay at rest. It doesn't matter what the gravitational field strength of whatever planet you're on, this will still stay at rest. So we've actually found something kind of universal. Does anybody know what sine over cosine actually is? It's tangent, if you do some trig identities, and you'll learn that this year. You don't need to know that, but this would be how you can calculate minimum stickiness on your shoes, for example, if you're someone who's going to be building roofs and you know they're going to be at a 21-degree angle. It's going to be sine 21 over cos 21. Which is what? Now, this half of the room, can you all go sine 21 divided by cos 21? This half of the room, can you all go tan 21? And you'll see we get the same answer. For both of them, you get 3.838. Oh, 3.84. What are the units from you? Nothing. So that's a 3.84, 0.384. What's the unit for what? For mu? No units. The reason is to get the mu by, Matt, look up. Mu is actually friction over the normal force. If I get the mu by itself, it will be newtons divided by newtons. They're gone. Nothing left behind. I like example 8, I like example 8, I like example 8. Example 8 is a nice question. We are going to finish with this. I'm a little grumpy because I was wanting to give you lots of time to work on this and not give you much homework for the weekend. And this is really, 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 really key. I'm just trying to do some mental gymnastics here. Give me a second. Okay. Shedding a little money. Oh, and on cue, OneNote decides to be a little frustrating. Okay. We're going to pause here, but as a start, you can absolutely do number 2. Number 3. Number 5. Eight C and 8D. Nine. Ten B. 11. 11. 14. 15 is trickier than I'm going to ask, but see if you can figure it out. You're not going to get all of that done in class. Here's what I would like. There's about 8 minutes left. I would like you all to take a serious work for the final 8 minutes and get a lot done. Either stuff from last lesson or stuff from here today. Get as much as you can done. I'll pick up with this when I see you. When do I see you next? Tuesday in a week. Okay?